Hey everybody, welcome to the final video of the linear relations unit. Today we're going to be talking about using equations to graph and how to pick apart those equations, see what all the pieces are, how to solve problems using the graph and the linear relationship or the equation. So we're going to do all those things. Hopefully it won't be too long a video. I'm thinking it'll be about 10 to 15 minutes, so a bit shorter than the last one, thankfully. But it is very important. It is something that you're going to encounter frequently throughout high school. So with that said, let's get started. Okay, so we're going to start off immediately with a quick example here. I'm going to go through and talk about this entire graph and what makes sense on it. We're going to graph using a table of values. We're going to create ordered pairs, and we're going to talk about what's reasonable and what's not. The example itself is sound traveling through salt water. So it says right here that sound travels at 1,500 meters per second through salt water. And that can be expressed by the formula d is equal to 1,500 t. So d here means distance traveled. The distance traveled is 1,500 times however long it took, how many seconds, t. Start off, we make a table of values. So remember that the t here represents seconds. So here I have t, and that's going to replace my x. I'm not going to say x, I'll say t instead. And for my y, I'll be talking about distance traveled, so I'll put d. I'm going to talk about 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. They're just randomly selected ones. I could have done 1, 7, 2,000. It doesn't really matter. But 1, 2, 3, 4, 5 is pretty easy. So in 1 second, how many meters have been traveled by sound? Well, 1,500 because it's 1,500 meters per 1 second. So I can already just put that one in. And if it's per second 1,500 meters, then I just have to add another 1,500 to make it for 2 seconds. So that becomes 3,000. And then I can just continue on, 6,000 and 7,500. Okay. I want to talk briefly about the entire Cartesian plane here, what makes sense, and why I chose 1 through 5 here. So the first thing to consider is we're talking about time. Time, since we're not time travelers and we're dealing with something that's traveling through time, we're thinking about only positive values here. So it does not make sense to be considering negative values of time. We're not going to say, how far did it travel in negative 43 seconds? Doesn't make sense. So anything where time is less than 0, I don't need any of that. This is all garbage to me. Same thing with distance. Distance, since we're talking about something physical in the real world, we're talking about positive values of distance. We're not saying that after 5 seconds, sound traveled negative this much distance. It doesn't make sense. So anything where the distance is negative also doesn't make sense. That's not the case for everything, but in our example, we could just narrow it down to the scope of quadrant 1, positive values only. So I could have just given you a box here and said, let's just focus on quadrant 1, and that would have made sense here, but then I wouldn't be able to explain why all this other stuff doesn't make sense. But now that being said, let's move forward and start graphing. To graph, we need to make ordered pairs. So we have ordered pairs here where we just take the x value or the t value and the y value or the d value in this case and create a point out of each of these ordered pairs that we're making. So I'll just quickly write that in. After we finish this, we can start to look at our graph and find where those points would be located. So to do that, I'm looking along the t-axis, and my first point is 1. So I'm just going to say that each of these boxes represents 1 second. So 0 seconds, 1 second, 2 seconds, 3 seconds, and so on. So if 1 second is here, then my coordinate will be somewhere along there. However, at the same time, these are like big numbers. So if I say 1 meter is each of these, it just won't make sense. Because then I'm going to have it extend really far beyond my page. How about instead, since there are 10 blocks, I will say that each of these block represents 1,000 meters. So 0 to 1,000 to 2,000, 3,000, 4,000, and this right here is going to be 5,000. I'm kind of messy here. Let me erase. I'll make that a little nicer for us to see here. So 1, 2, 3, 4, 5,000, and here would be 10,000. And I might have to do a little bit of estimating with some of the numbers in between, but I think you'll get the point here. So 1,500 should be about here. 2 and 3,000 should be about here. 3 and 4,500. 4 and 6,000. And finally, we have 5 and 7,500. As you can see, these dots form a nice line. If I connected all the dots, it would create a line through them. And I'm going to try to do that, but it's really hard to do it with my hand here. Let's see. No, that's horrible. That's better. Oh, yeah. Real good. Okay, so we've got a line going in that direction. Okay, so we have graphed the ordered pairs in our table of values, and now we can talk about whether it's reasonable to have points between the ones on this graph. So just to emphasize, let me redraw some of these points here so that they stand out. Okay. So the question is, remember this is 1 second, 2 seconds, 3 seconds. Can I have a point in between here? Does it make sense to say, hey, what about right here? In 1.5 seconds, we've traveled this many meters. Does that make sense? Think about that. Sure, why not? Absolutely makes sense. I could say I traveled 2,250 meters in 1.5 seconds. Sure, makes perfect sense. Remember back to the previous video, we talked about discrete and continuous. This is an example of a continuous graph because it makes sense to put numbers in between decimals or partial values. They absolutely make sense. It would not make sense in a discrete one where you're like, okay, there are 10 people every day entering a store, more than before. So like 10, 20, 30, 40, it's growing. But we can't say there's half a person. That's a discrete value. We can't say that 2.5 people more entered the store today than previously. You can't have half a person. Just like that pizza example from before. We're talking about calling into a pizza place and saying 1 topping, 2 topping, 3 topping pizzas. You can't call them and say we want 2.5 topping pizzas. No, they won't do that. All right, because that's not part of their menu. So this is an example of a continuous graph, and it is reasonable to have points in between. Now, knowing that, we are going to calculate the distance sound travels in 3.5 seconds. And in this case, we're going to do it graphically. There are lots of ways we can do that, but here we're going to do it graphically. So if 3 seconds is there and 4 seconds is here, I can look at my graph and I can estimate here what that number would be. It's going to be a number between 4,500 and 6,000. So it's somewhere between these two numbers. Okay? And it's equal distance because it's 3 seconds and 4 seconds. 3.5 is right in the half of there. So if I know that it jumps from 4,500 to 6,000, that's 1,500 distance, and I'm going half of that, well, I'm going to be adding 750 to this number. So I'm expecting 5,250. And estimating on my graph, I'll see that, right? 5,250. It's hard because I'm kind of scaled in a really terrible way, but it makes sense. 5,250, 5,500 would be about here. So sure, 5,250 meters would be my answer for D. All right. Let's move forward to a new one. And this is a show you know example. So what I have here is Paula renting a lawnmower for $8 per hour. And I'll fix this graph here because we are talking about time again, T. and C represents your cost. So the formula for this is C, the cost, is equal to 8 times T, where C is the rental cost and T is hours. You're going to make a table of values first, then you are going to graph the ordered pairs, and then you're going to think about whether it's reasonable to have points in between, and you can calculate the cost for 12 hours. And I want you, especially on this one, to consider whether it's reasonable to have points between those based on the fact that she's renting a lawnmower. Okay, that's important. All right, so pause the video at this point, and we are going to check through your answers in a very short minute here. Okay, you should have unpaused and tried this out yourself. And here is what I plotted. So you might have chosen different numbers. I chose 1 through 5 again, and I just put my values in my graph. I've got a line here that could be created, and I chose that each of these boxes is worth 5. So that's how I scaled it so that it would fit nicely. So table of values done. Yes. We graphed. Yes. Is it reasonable to have points between the graph? I mean, the thing here is it makes sense logically that you could rent a lawnmower for an hour and a half, for example, or 2 3/4 of an hour. But you're renting it. You're renting it from a business. So realistically, the business probably charges you per hour, just like it says here. So in that case, it doesn't make sense, because if you use something for 2 3/4 of an hour, they'll charge you for 3 hours. They're not going to prorate it for you. So it doesn't make sense, but it kind of does too. But in this case, I would say maybe, but for the fact that it's a business, I would say no. Calculate the cost for renting 12 hours. I put 12 times 8, so 8 times 12 hours is equal to 96. So $96 for 12 hours of rental. Okay, example 2. This one I'm doing with you. Linear equation, y is equal to minus 3x plus 4. Y is equal to minus 3x plus 4. I'll just write it here so it's bigger. Make a table of values. Use positive and negative integers and zero values for x. Okay, so what I mean there is, in the previous example, we're just thinking about positive time. But that's not always the case. There are negative examples too. So I'm not only going to choose 1, 2, 3, 4, 5. I like to do like a spread. So I might do -2, -1, 0, 1, and 2. Or maybe -10, -5, 0, 5, 10. I like to do things like that because it gives me a better spread. If you choose all these numbers that are real close together, sometimes it can be too squished. You can't make a line very good. So you can try other points as well. Depends on what you're trying to do. So we're making a table of values. The way that I'm going to do that is I choose an x value I want to test, put it in, substitute it in, and see what my y value is going to be. So I put in an x, and then out comes a y. Let's try that idea out. We'll try it first with the -2. So I've got y is equal to -3, and I'll put -2 in for x, and then plus 4. So here we go. -3 times -2 is positive 6, plus 4 is equal to 10. So my y value here would be 10. Now I can try it with a -1. Let's change that. So I've got a -1 here. So -3, whoops, I erased the wrong thing here. So -3 times -1 is actually positive 3, sorry. And then positive 3 plus 4 is 7. Okay, so I've got 7. I like this one better. One of the reasons I like doing 0 is, and especially 1, is that it works out really nicely. If I throw a 0 in here instead for x, I get -3 times 0 is just 0. So I get 0 plus 4, well, that's just 4. Okay, let's try 1. -3 times 1 is -3. -3 plus 4 is positive 1. All right, and the last test value that we're going to do here is positive 2. So positive 2 times negative 3 is negative 6, and I end up with negative 2 here. Okay. Now that I've done my table of values, I have a fair number of points here that I can plot to make a line. So negative 2x is 10y. Negative 1x is 7y. 0x is 4. 1x is 1y. And 2x is negative 2y. So if I did that all correctly, it should line up to be a very nice line here. If I had plotted one of them wrong, like that, it would have looked a little bit weird, or it would have been non-linear. But fortunately, I didn't have that problem, so I've got a nice line. That's not it. That's not it. That's not it. Come on. That's closer. I've got a nice line that is going like that. So we have created table values. We've graphed the ordered pairs. Remember that these are the ordered pairs here. So just like this. And it does help to get in the habit of writing those out as ordered pairs, because that's usually how you're going to see them. And we need to determine the value for y in the ordered pair x is equal to 11 and y is something. All right. Unfortunately, I can't really do it graphically very well because I don't know how to draw a straight line on here. But you might be able to do it graphically, and if you were, it would stretch out somewhere like here-ish. I don't know, maybe here? Or, wait, no, x is equal to 11. That's way off my screen. So I can't even do it. I was looking at y is equal to 11. This is going to go all the way down here and then beyond down, way down there somewhere. So I can't do it graphically with the scale that I did. If I shrunk it, maybe I made each of these boxes equal to 2 in either direction, or for the y, it would have possibly worked out a lot better. But I'll show you another way now, because you can probably do it graphically by now, just from the previous example. It's not a very difficult strategy. But we do also have our equation of the line. So we can use this to find out our value here. So if we are looking just for an extra point here, where x is equal to 11, let's just put 11 in. That's just an easier way to do it. So we've got minus 3 times 11 plus 4. Let's see here. Y is equal to minus 3 times 11 is minus 33. We have plus 4. And then all we got to do is do a positive integer and a negative integer added together. We get minus 29. So minus 29 would be the answer for y in that part there, part C. Okay. Oh, all right. So here is some tricky business here. And I am going to turn this into a show you know. And I do want you to pause the video and try to attempt this after I give you a couple hints here. The first things that I want to point out is I hinted that we're going to be talking about something called Slope-Intercept Form. Slope-Intercept Form is this. You'll see it a lot as y is equal to mx plus b. And you'll notice that this says y is equal to ax plus b. I mean, it's the same thing. They're exactly the same thing. The a is the m. It's just a different way of showing it. But usually you'll see it as m. Okay? And m, or a in this case, refers to something we call the slope. So the slope goes here. And we did talk about this before. Slope is rise over run. It's talking about how much something goes up or down based on a step to the right, or a couple steps to the right, or whatever. So we can figure that out. We can figure out the slope, the m, the a. We can figure that out just by looking at the steps between points. So here's an example here. X here starts at minus 1 and it goes to 0. That's a change of one step to the right. The y, for that one step to the right, goes one step up. So let's see if that continues. One step to the right, one step up, one step to the right, one step up. So my slope here is rise over run. I'll write that out here. Rise over run. My rise is the y value. How much does it go up for every step? It goes up 1 step for every step right. So my slope is 1 over 1, or 1. I'll just write that here. My m is equal to 1. Let's try one more here, and I'm going to leave the rest for you. So this goes, look at this one right here. If it's linear, then if that steps 1 to the right, this stepped -2. So it went 2 down for every step to the right. Rise over run. My rise is -2. I guess that's like a fall, but we still call it a rise. So -2 is my rise for every 1 step right. So my m, or my slope, is -2. And I can check that. For every step right, I go down 2. Okay? That should be enough to find slope. Now the other piece of the puzzle, that you're missing is the b. So we covered this. Now we're looking at b. And the b is something we call the y-intercept. The y-intercept is the point where on a graph your line crosses the y-axis. All right, so it could be there, or if you have a different line, there it is. Or you have another line, it's right there. It's the point where it crosses that y-axis. And the important thing about that is the y-axis happens when x is equal to 0. This is my favorite, because when x is equal to 0, everything, well, not always, but usually things are very easy. So let's look at our table here. We can spot x is equal to 0 right here. So already we can just say our y-intercept, our b, is equal to 2. Here, same thing. There's our y-intercept, because x is equal to 0. So our b is equal to 2. Once you find those two things, you have the equation of the line. The equation of the line is y is equal to mx plus b. M is the slope. I showed you how to find that. B is the y-intercept. I showed you how to find that. The y and the x are just y and x. They change for every point. So you would leave it, for example, as y is equal to, what was the slope here? I think m was equal to 1. So 1, and you leave the x alone, plus b was 2. So the equation of that line is actually just x plus 2. Y is equal to x plus 2. All right, that's a lot to think about. That's a lot to cover right now. So it's kind of an introduction to something you'll be doing in the future. You don't have to understand everything here, but you should be able to find out what the steps are in between. You should be able to notice that. Okay, you should be able to spot for every 1 step to the right, how much does it go up or down. That's very important. And you should also be able to find the slope, the y-intercept, just by finding x equal to 0. You should be able to do those things. So here's a good point for you to pause the video and test to see whether you can do this on your own, whether you can find the equation of the line, or at the very minimum, just the slope and the y-intercept. So go ahead now, pause the video. Okay, I'm going to scroll forward here, and I'll just line out what I put for my b and for my a, or my slope. I got this for that one, and that's that one, and that's that one, and this is that one, and this is that one. You'll find, I think, that this one didn't have a x value for 0, so you kind of have to fill in the details. If you notice that it's going from 2 steps to the right, 2 steps or 4 steps to the left, then you know there's something in between here, right? You could just figure it out just by the other points, and you should be able to do that one. Everything else, they're all kind of laid out for you. All right, we're near the end here. I've already pointed out slope and y-intercept. That's great. We are trying to write the equation that relates the x values to the y values. It's the same thing as we did in the previous one. We are just trying to find the slope, m, and we are trying to find the y-intercept, but we're going to do it graphically this time instead of with a table of values. Let's start off with our b, our y-intercept. Remember, the y-intercept is when x is equal to 0. So we're just trying to find on this line where it crosses the y-axis. And obviously, it crosses right here. So our b is just 4. Easy enough. Our slope, though, is rise over run. So what we want to do is find out how much it goes up or down for every step right. We could do it a couple different ways. Sometimes the values are going to be weird. We could just choose any points here. Let's choose this one. It starts off right here at 0, and let's take one step to the right. That could be 1, right? It could be a value of y is equal to 1, but it's not a super clear value. So I don't know for sure if I choose that I'm going to be right. So what I'm going to do instead is I'm going to pick one that's very clear. Let's choose this one, this -2 value. So let's say it went from 4 all the way down to -2. That's a change of 6 to the negative. So it went down 4 and then 2 more, so that's -6. So my rise is -6, but it's not for one step to the right. That was actually for 2 steps to the right. So my slope is -6 over 2, and simplifying that, it's -3 over 1, or just -3. Okay? And what I want to point out here is that graphically, we can see in a couple different places that for every one step right, it goes down 3. So it went from 7 down to 4. That's down 3. And look at this. One step right, -3. -3, one step right. Okay, and it kind of continues. So you can always look at it like that as individual steps. But at the same time, we can double a step. We can say for 2 steps to the right, 1, 2, it went down -3 and -3, so that's a total of -6. Right? So they're equivalent there. Now I have my m. And I have my b. With this information, we can create the slope-intercept form of a line. Remember, the y and the x are just y and x. So y is y, m is -3, x is x, and b is 4. This is our equation of the line that relates to the information we have here. Here's a show you know. So pause the video here, do the same thing I just did, make a table of values, graph the ordered pairs, find out what are the coordinates for the point that would lie on the y-axis. So that is your y-intercept. So I want you to find your y-intercept, and you can challenge yourself too to just point out what the slope would be. You should be able to find the y-intercept just by doing numerical stuff too, but you can find it graphically if you prefer. Go ahead and pause the video and tell me these things. Here's what I got. So my y-intercept, where x equal to 0, is right there, 0, 3. And the table of values there, I've graphed all these points. I can also say that my slope, m, is 2. So 2 over 1 or 2. Okay, we are done. So it is time to stop. This is the end of this unit. And we will have, I think the next one we're doing is Pythagorean theorem. That should be fun. Okay. See ya.